Ladies and gentlemen, welcome to today's webinar organized by the Department of Physics, Ramakrishna Mission Vidyamandira, on Long Roads to Black Holes, From Mysteries to Reality by Professor Supratik Pal from Indian Statistical Institute, Kolkata. So before we begin, I would like to request respected Principal Maharaj to address today's meet. Over to Maharaj.
Om Namo Bhagavate Ramakrishna. So, on behalf of Ramakrishna Mission Vidyamandira as well as the Physics Department, I welcome Professor Supratik Pal to today's webinar. Actually, he is not at all a newcomer. I don't know whether you people, our current batches of students, whether they have seen Professor Pal or not. Earlier, at least 2 years back, 2 or 3 years back, he used to come here regularly and take classes. And incidentally, he happens to hail from Ramakrishna Mission background as well. He was an ex-student of Ramakrishna Mission Vidyapit Purulia. And incidentally, I was there working with him for at least 2 or 3 years at that time, early 2001, in that period of time. So that was days of happy memory. And on behalf of Vidyamandira family, I once again welcome Professor Supratik Pal. He has done his PhD from Jadavpur University, and later on he completed his postdoctoral research from IUCAA Pune, and of late he has received the Young Physicist Award from Indian Physical Society. All these things possibly our Nishnad will be covering, but anyway, these are things of which we boast of. We feel very much proud, so I felt tempted to share with the rest of my friends, our dear students. Welcome, Professor Pal.
Thank you, Maharaj. That was indeed nice. Well, curiosity indeed is one of the greatest secrets of happiness, and of the most fascinating subject that makes us curious is our universe itself. Today, we are fortunate to have among us Professor Supratik Pal, who will lead our imagination towards one of the mesmerizing components of the universe, the black holes, unveiling the mysteries and leading us towards reality. Now let's have a few words about his scintillating personality. Professor Pal, who dedicated his life in cosmology and astroparticle physics. Professor Pal had his PhD from Jadavpur University, followed by postdocs from Inter-University Center for Astronomy and Astrophysics, Pune, and University of Bonn, Germany. He was awarded the prestigious Alexander von Humboldt Fellowship of Germany twice, and the Platinum Jubilee Fellowship from ISI Kolkata, and the Young Physicist Award from Indian Physical Society. He is currently involved in 2 mega projects. He is the member of the consortium CMB Bharat, a proposed Indian space mission for cosmic microwave background observation, and the member of scientific and engineering team, and also member of the Executive Council and Science Subcommittee, SKA India Consortium, a part of the Square Kilometre Array Telescope. Now, I request Professor Supratik Pal to shed some light on this exquisite topic and fulfill the hunger of our curious mind. Over to Professor Pal.
Thank you very much for a nice introduction. So can I share my screen right now?
Yeah, sure.
Okay. Yeah, so can you see my slides?
Yes, sir. Yes, sir.
Okay, that's good. So let me switch off my video and go back to the presentation mode. Yeah. So is this all right? I hope I'm both audible and visible. So
yes, sir.
Let me thank once again to the members and the Principal Maharaj of Ramakrishna Mission Vidyamandira, Belur. As you have already heard about, I have been a frequent visitor to that place and had, so that place is pretty close to my mind. So it was my great fortune to be associated to this organization for quite a few times. And as I'm also from Ramakrishna Mission background, so I fear the same feeling. I basically share the same feeling with you guys. So today, what I'll try to do is that I'll try to basically give you the historical perspective of the development of this fascinating subject called black holes. All of us have heard about these things to some extent. So I'll try to explore both the mystery aspect as well as the experimental aspect of these two things, and I'll basically try to make a synergy between them. So as you know, physics is an experimental subject. So in this subject, basically theory and experiment, they go hand in hand. So I'll try to discuss first the theoretical aspects based on the mystery part, so to say, and then I'll discuss the experimental aspects, and I'll try to make the synergy between them. And incidentally, today is International Astronomy Day, and it's a great fortune for me to give a talk on this most interesting and fascinating and most surprising astronomical object called black holes. So I try to keep my talk as simple as possible without going into technical details. I'll assume that most of the audience over here are UG level science students. So I'll try to focus my talk onto that. So I'll assume that you have high school kind of science knowledge. Even if you don't have, doesn't matter, because I won't discuss any mathematical expression or nothing like that. So I'll mostly show you some pictures and diagrams, and I'll basically give you some descriptions of the scenario without going into the technical details of the mathematical aspects of black hole. So this is the basic target. Okay, so in the next 1 hour or so, I'll be basically discussing with you this fascinating subject. And before I go into the details of my talk, so this talk is basically a tribute to these two persons. As you know, I mean, I'm pretty sure all of you know about these two persons. The guy Albert Einstein, based on whose general theory of relativity, this subject called black hole, its theory and experiments, everything have been developed based on his theory. And the guy sitting on the right-hand side, I'm pretty sure all of you know about him. So this was the 160th, pretty recently we observed the 160th anniversary, birth anniversary of this guy. So these two guys, basically, as you will see during our discussions, they basically share the thought process of our discussion, and they basically more or less control our mindset towards this direction. So this is my small tribute to them. Okay, so let's begin with this precise description of the Nobel Prize Committee. Why I am telling you this? Because primarily I've chosen this subject because this subject, black hole, is 100 years back. As you will see, it's a long history. I'll discuss this long history slowly and slowly. But very recently, only in the last year, the Nobel Prize in Physics 2020 was given to black hole physics in general for the first time. So even though we know about this entity for the last 100, I think more than 100 years or so, I'll come to that point. But very recently, it was the Nobel Prize Committee basically appreciated that. And why that is important, because I'll come to that. I'll try to explore those things. I'll try to unfold these mysteries slowly and slowly. So basically, so let me just read out within quote unquote, the citations of the Nobel Prize Committee. The Nobel Prize in Physics 2020 was divided. One half was awarded to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. So don't go into the names and all these things, and don't get confused with these things. I'll try to explain these things slowly and slowly. All it tells you is that this guy on the left, Roger Penrose, he developed the physics of black hole, the explanation of all these things, and he proved that, I mean, along with others, I'll come name slowly and slowly, he proved that the black hole formation is an inevitable thing in general theory of relativity, which I'll discuss slowly and slowly. And then the other half was jointly given to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. Once again, I will explain all these names slowly and slowly. But all it tells you is that the guys on the right-hand side, Genzel and Ghez, they basically led the experimental side of discovery of black hole, and they, for the first time, I mean, I'll tell you some indirect evidences of black hole detection later on, but they, for the first time, they detected, I mean, they did not detect black hole as of now, I'll tell you what they detect, but for the first time, they give you a direct evidence of having some supermassive compact object, which we'll call black holes later on, which is located at the center of our own galaxy, Milky Way. So because of that, even though the theory of black hole is known for the last 100 years or so, since the discovery was done pretty recently, I'll tell you the time and all these things. That is why the Nobel Prize committee basically gave a Nobel Prize to these guys only in the last year, and that is why the field is even more exciting today, because at the end of the day, this has been appreciated by the Nobel Prize committee. Okay, so let's begin from what we know already. Okay, so for sure, all of you know about this from your high school kind of knowledge, that this is our solar system, which has got sun in the center, and we have 9 planets which are rotating around the sun, and our own Mother Earth, that is only the 3rd planet, which is rotating along with its sisters around the sun. This is something we know from our high school kind of knowledge. But if you go back to our scientific understanding, then it was not known to us from age-old theory. Okay, only around 400 years back, one guy called Nicholas Copernicus, and then later on a guy called Galileo Galilei, they proposed, and then Galileo Galilei basically experimentally proved that this is indeed true, that in our universe, the Earth is not in the center. So it's not a geocentric universe. This was the previous idea that was basically prevailing for the last for the previous hundreds of thousands of years or so. But right now, from experimental evidence, for the first time, these 2 guys said that in our universe, the Earth is not in the center. At least in our solar system, we see that sun is in the center, and all the other planets, these 9 planets, along with the Earth, they are rotating around the sun. This is something we know from our high school kind of knowledge for sure. But then, shall we stop over there? No. Because, as we know, even if we are not a science students, we know, even if we are laymen, we know from our day-to-day perspective that if we look into the outer space in the night sky, and if the sky is really clear, there is no much noise, there is no cloud, there is no light pollution and all these things, then even in our naked eye, we can see millions and millions of bright objects in the sky. And we know, of course, from our high school kind of knowledge, that each bright object represents either a star or a star-like object. I'll talk about those objects slowly and slowly. But for sure, from our high school knowledge, we know that these bright objects, they are located outside our solar system. So it's a huge amount of universe, which is unknown universe, which is located outside our solar system. And this information, this kind of knowledge, this is basically haunting the civilization for several years, that what is there in the outer universe, and how we will be able to know about them in details, in more scientific knowledge, with vigorous details and all these things. Is it at all possible to know about that? So this is haunting the civilization for several years. Even this haunted Galileo and Copernicus to develop this idea, and then to experimentally verify that thing. And in order to do that, what people do is, I've already talked about that, this guy called Galileo Galilei, he first built something, an instrument, using which we can go beyond our naked eye. So, as all of us know, our eye is a lens. And since this is a lens, this is an instrument, it has got limitations. So, we need to go beyond that limitation. So, we need to overcome the limitation. So, in order to overcome that, what people did is they cleverly built an instrument called telescope, and using the telescope, if we look into the outer space, we can look much beyond what can be seen using our naked eye. And that will basically increase our curiosity, and at the same time increase our knowledge about the universe, and at the same time we'll try to explain whatever we see and whatever we don't see as well. I'll come to that point. I'll basically try to develop the state-of-the-art development of this theory in the next 1 hour or so, as I have already told you. And here is the cartoon of the telescope, as all of you know from your high school kind of knowledge. So it's something which Galileo discovered, for example. So this is the cartoon of the telescope. But over the last 400 years or so, science has developed, human knowledge has developed, technology has advanced. So right now, we are much more competent compared to what we have been capable of 400 years back. So right now, what we have done is that we are basically armed with several advanced and highly sophisticated level telescopes. These are hundreds in numbers, but I will not talk about all of them in details. I will mostly focus on a couple of them which are important for today's discussion. So Using the telescopes, what do we do? So we can basically, so let us discuss this in a bit details before going to the main topic of our discussion. So right now we have hundreds of telescopes and we have plethora of data that are coming from the outer space, and we're trying to catch that data using our telescopes. How we can catch that? I'm pretty sure from your high school kind of knowledge, you know that we are basically using our telescopes, we are basically catching some waves, basically. And these waves have two very, very fundamental properties. What are those properties? One is the wavelength and other one is the frequency. And if we multiply these two, we get the typical speed of the wave, the velocity of the wave. And you know, based on these wavelengths, whatever wave is coming, we're trying to catch those waves using our telescopes. And those waves can have different kinds of wavelengths. Like the optical wavelength, we know for sure how much is the optical wavelength. This is typically of the order of 10⁻⁴ centimeter, the Vibgyor. Okay, that is the optical range, the wavelength range that we can see using our naked eye. So the waves of which the wavelength is of the order of 10⁻⁴ kind of centimeter kind of things, that in order to catch those, we built telescopes which are optical kind of nature. A cartoon has been shown just in the previous slide. So this is the optical telescope, but in our universe it has been found that there are lots of other waves of which the wavelengths are either smaller than the optical range or larger than the optical length. So in order to catch them, an optical telescope, the typical kind of telescope you are used to seeing in your school days and all these things, they are not compatible because they are only capable of collecting waves of optical bands. So in order to catch them, we build different kinds of waves based on wavelengths. Some of them are soft X-ray, hard X-ray, infrared, and there are larger side of the optical wave, which are radio wave, or a part of that is called microwave. I'll talk about some of them in a bit details later on. So there are hundreds of telescopes, as I have told you, and based on location, where exactly the telescopes are located, based on that, we can broadly categorize these telescopes into three categories. One is ground-based, the other one is underground, and the third one is space-based. And of course, we have hundreds of telescopes in these categories as well. I'll just give you a very few and very well-known representative of each one of them before going into the main topic of my discussion, just to motivate you guys about the theory and the experimental side. So for the ground-based telescopes, the most two, I should not call they are the most two important, but they are pretty exciting telescopes as of now. The number one is called Vera Rubin telescope. That telescope looks something like this. This is still in the construction stage. We hope to get the first, this is in the Chile, and we hope to get the first result starting from 2023, which is not far away. This goes by the name of the famous astronomer Vera Rubin, who first discovered the evidence of dark matter in our any spiral galaxy, including our galaxy as well. So this goes by the name of Vera Rubin. And the second one is called 30-meter telescope. This one looks like this. This is still in the planning stage. Okay, the proposed site is somewhere Mauna Kea in Hawaii, and we hope that by 2027 this will be complete and the data will be starting to come. But before going to the other things, let us just stop for a minute and try to think about this. This is called 30-meter telescope. Why this is called 30-meter telescope? Because it's a combination of mirrors and all these things, and the effective diameter of the mirrors will be of 30-meter distance. Just try to imagine, it's about the size of a big football ground. So we are capable of seeing about our universe with a huge kind of mirror, okay, of which the effective diameter is around 30 meters, which is around the size of a big football ground. So we'll be able to do that thing within a few years or so. So this is being done on the ground-based side. About the space-based side, I'm pretty sure all of you have heard about this particular telescope, and that's why I have shown this thing over here. Though we have hundreds of other space-based telescopes in our operating there. So this is a particular telescope which was proposed long back, and this has started functioning in 1993, and this is giving us huge amount of data for the last 27 years or so. So basically what it is doing, it is basically rotating around the Earth in a stable circular orbit, and it is collecting data from the outer space and transmitting to that data to the receivers on the Earth's surface. So we are collecting that data and we are basically decoding that data. I will tell you the decoding technique later on, albeit qualitatively, but just try to stop a bit and try to explain it. Okay, This is the surprising thing. This is just around 10% of this Hubble Space Telescope. And if you look into this telescope carefully, you can see a guy sitting over here. So if you consider that this guy is, say, 6 feet long, and this is just around 10% of the telescope, with all these technical details, lots of instrumentation and everything is there. So you can imagine about the total size and total technological difficulties of this telescope, and you can just stop a minute and appreciate the power of human intelligence and excellence, that all these things have been basically thrown to the outer space, and it has been put to a particular orbit with all these calculations, and it is rotating around the Earth for the last 27 years with any stop, any stage, and this is giving us huge amount of data. And as I said, this is just a representative of space-based telescopes. We have hundreds of other telescopes, but I won't go into the details of that thing right now. This is the third example of underground telescope. This is called South Pole Telescope. And if you look into this telescope looks like this. Come on, this is not that impressive, right? I was giving you so much beautiful and nice picture, and right now I'm just showing you a huge amount of pile of ice over there on the South Pole. So why we cannot see them? If we zoom in, we can see that this looks like this. So why you cannot see them? Simply because everything, the entire telescope has been put inside the South Pole at a distance of more than 1 kilometer inside the South Pole. So everything is there inside. That is why this is called underground. And you can just see the tip of the telescope, which is located over there. So these things are basically, so all these telescopes, some of them are underground, some of them are ground-based, and some of them are space-based. All of them, the basic target of placing all of them is to extract out information about the outer space by collecting different kinds of waves. Depending on what kind of waves we are catching, we'll build our telescope. I'll come to that point later on. Okay, and that will be basically discussed today in a bit details. So we are basically catching that data, and we are trying to analyze that data, explain that data using our scientific knowledge. I'll come to that point slowly and slowly. So coming back to, once again, coming back to our universe. Okay, so we have talked about a little bit about our telescopes. I'll once again come to the telescope part later on. But this is what we have been able to see using those telescopes. So where we actually stopped? We stopped at the point that we know about our solar system for sure. And using our naked eye, we can see there are millions of stars on the outer region outside the solar system, which we are going to explore. Okay, and using this telescope, first and foremost, we have been able to see this thing, which is called Milky Way. Its typical scientific name is galaxy. This is our galaxy. Why I call it our galaxy? Because as you can see, there are millions of dots over there. Each dot represents a star. So what is our sun? Sun is just a dot inside this galaxy, which is a collection of millions of similar stars and star-like objects. Many of them are even much more bigger than stars, and this will be very important in today's discussion of black hole, as I'll show you later on. So this is our own galaxy, which is called Milky Way. And once again, you can stop and think over this, that we have been already discussing our huge solar system, and now we can see that this solar system is nothing but a only small white dot inside our Milky Way galaxy, which is a combination of millions of stars and star-like objects and other things. So it's a huge kind of thing we will be able to talk about. It has something else inside its center. I'll come to that point later on while discussing black holes. But before that, let us once again stop and imagine about that. Now I'm talking about our universe. And as you see here, every extended object is a galaxy. So our universe is basically made up of millions of galaxies, of which one galaxy is our own very own galaxy, which is Milky Way, inside which there are millions of stars. Out of them, only one is our sun, and we are basically living on a very small planet which is rotating around the sun. So we are basically located at somewhere which is a negligible region inside this big huge universe, which is a collection of millions of galaxies. Not only that, these galaxies play the building block. They play the role of building block of our universe. Okay, so I'll discuss this in detail. So what I want to say right now is that using all our telescopes and all our technological sophistications, we have been able to know about very far away about our universe very precisely. All these galaxies and everything. We can go beyond galaxies. They are called clusters. We can go even further away, which is called cosmic microwave background observation. So all of these, I'm just giving you some names. I'm not going into details of all these things because that is not my target today. But using our telescope, I'm just trying to convince you how much we have developed so far as science and technology is basically concerned. So we have been able to know all about them in much more details than what you can see in this slide. I'll come to those details slowly and slowly. So right now, my point of discussion will be these galaxies, including our galaxy, Milky Way. Okay. So I am discussing this thing. In order to discuss about that, let me go back to once again a particular telescope, which is called Event Horizon Telescope. That plays a very, very crucial role so far as the Nobel Prize in 2020 is concerned. So that's why I'm discussing it in a bit details. And this will, I do hope that this will also give you some impression of how developed the technology is. So this is called Event Horizon Telescope for a particular reason. I will explain later on. But first of all, try to think about that. This is a combination of 11 radio telescopes around the world. So it's not a single telescope. I'll explain what do I mean by radio telescope later on. So for this moment, let's forget about this terminology, radio telescope, and focus on these things, 11 telescopes around the world. So you can see in the map, these telescopes are located at different continents. Some of them are in the North America, some of them are in South America, some of them are placed in far west, that is in Hawaii, some of them are in Europe, some of them are in Africa, and even if you go long south, towards the long south, there is South Pole Telescope, of which I've already talked about. So each one of them is a complete independent setup of its own. I'll talk about them later on, but there is a synergy among all of them. See how science is going on. Whereas the rest of the universe, the politicians and rest of the others, they are basically trying to fight with each other among countries and within the countries and all of these things. Scientists are basically trying to join hands with each other, and they're trying to develop about our knowledge base and about our universe as a whole by basically exploiting the individual resources. So here what they are doing is that these 11 telescopes, which are located at different places, they are taking data individually and then they are combining the data. And these combined data basically helps us know about black holes to a great extent. I'll come to that point in a minute. Okay, but before that, let me focus a little bit on that. Okay, just to give you an impression about each telescope, these are the telescopes. I just zoomed in. These are each telescope which goes by different names. Some of them are SPT, ALMA is there, APEX is there. I mean, for the science students, you may come across some of the names in your popular science lectures or newspapers or anything else. So that's why I'm giving you these names. So each one of them are this. And if I zoom in further, then this looks like this. So right now I'll explain what do I mean by radio telescope. As I said, each one of them is a combination of, so each one of them is a radio telescope, and overall, the entire Event Horizon Telescope is a combination of all these 11 telescopes. So here is one single radio telescope which is located over there. Says whatever you call it. So one of them, these 11 telescopes. So what do they look like? Do they look somewhat similar to an object which you have seen in your day-to-day life? I'm pretty sure, had you been in front of me, I would have asked this question, and all of you would have suddenly shouted that yes, we know about this guy, pretty sure. Because this is nothing but a disk antenna we use in our day-to-day life to set elevations. Albeit the fact that these disk antennas we are using over here, they are technologically much more complicated and much more advanced than a disk antenna you use in your day-to-day life. But just to keep in mind, they have the same theory over there. Because in disk antenna, what do? You basically catch the waves, catch some waves, and those waves you cannot see. They're not optical, right? Those waves you cannot see. Their wavelengths are much bigger compared to the optical wave. So you catch those waves, and those transmissions are basically being done and being shown, and so you basically watch the television, and you listen to all these things over there by those transmissions. So here also the target is to catch those waves of which the wavelengths are much bigger than the optical range, and by these radio telescopes, and each telescope is not a single disk antenna, so to say. Each one is an array of several disk antennas located at different angles depending on what kind of physics we are going to study. So each one, so right now, what is Event Horizon Telescope? Let us summarize that it is a collection of 11 radio telescopes located all through the world. Each radio telescope is a collection of arrays of disc antennas, and one such array is being shown in this slide. So it's a huge collection of instrumental development and all these things, and using these basically, we will basically come to the experimental side of black hole slowly and slowly. So this is the first slide of experimental thing that we have been able to observe. As you can see from here that this was observed, as I said, this is a pretty recent phenomenon. So this was observed only in April 10, 2019, just 2 years back. And what did it give you? It gives you an image or shadow, honestly speaking, this is called shadow, of the outermost surface of black hole, which is found in a galaxy which is called Messier 87. It's not our galaxy. I'll come to our galaxy later on. But this is a representation of a black hole. Just I'm trying to focus on this point because sometimes this is quite misleading. Sometimes you hear or you read that we have been able to see black hole. No, we have not yet been able to see black hole. Why we have not yet been able to see, why we cannot see black holes, I'll come in a minute. But what we have been able to see, and that has confirmed the existence of black hole for sure, is the outer surface, is the shadow of the black hole using this telescope. And this shadow is generically in the scientific language, this is called event horizon. For some reason, I'll come to that reason later on. Once again, let me repeat, we have not been able to see this in optical telescope because the yellow and red color, what we see, just inside you see a black thing. This is the black hole. Okay. Outside this, you see yellow and red color. These are visualized not in optical region. Okay. These are visualized in radio region. So that's why these are slightly color coded, so to say, depending on the temperature and all these things, these are color coded. So this is called radio eye. Using our radio telescope, using our radio eye, we have been able to see just the outer surface or the shadow of the black hole only 2 years back using all these 11 different radio telescopes around the world. Combinedly, we have been able to see this. Okay, and this is pretty exciting because, hold your breath, not only this we have been able to see, but using the data, because this was functional from 2019 onwards, we have been able to collect all this data and we have been able to see how basically black holes, I mean the outside region of black hole, which I called event horizon, that basically evolves. Honestly speaking, the last two pictures, they are the real images, but before that, those are not real images. They are basically done by using some simple geometry and all these things, which is called morphology. I'll explain why we have from 2019 to 2013. These pictures have not been directly seen. They are basically explained using geometry and morphology. I'll come to that point later on. But for sure, the 2017 data, that is something that was observed. In a bit details, I'll come to the details later on. So pretty exciting, as I was talking about, because black holes, they are in the vogue for the last 100 years or so. I'm going to explain those things. But very recently, after more than 100 years, we have been able to see them for the first time. So we're living in an exciting time for sure. Okay, forget about coronavirus and all these things. The universe is going, the world is basically going through pretty difficult times for sure. But during this time, the take-home message is that we are living in a very, very exciting time so far as scientific research is concerned. I will talk about the excitement slowly and slowly. But as I said, for the first time, pretty recently, we have been able to see, we have been able to find out direct evidence of black hole just by seeing the shadow, by seeing the outermost region of black hole, so to say. Okay, so is this all? I'll come to that point slowly and slowly. Before that, let me go back once again about so this is the experimental side I have talked about, just to motivate you guys about the thing that whatever we are talking about is not simply a theory thing. Okay, this is an experimental phenomenon. This has an direct experimental evidence that we have been able to see. I will talk about other experimental evidences slowly and slowly. But before that, as I said, I will basically try to unveil the mysteries and history of black hole for the last 100 years or so. So here is, let me spend some time on that. And before that, so this is pretty technical thing, the mathematical aspects. I'm trying to basically avoid those mathematical aspects, and I'm trying to basically explain everything in terms of some figures and some statements, so to say. So just please hold on for the next few minutes and try to follow some of statements that are being given over there, after which once again we'll come to those exciting experimental things, which I'll show by some pictures and some videos, real life videos and all these things. I'll come to that point later on in next 5 minutes or so. Okay. So before that, let us discuss why I call this a mystery. Okay, why I call black hole is a mystery. So let us try to unfold the mystery of black holes, starting from 1915. In this year, basically, Albert Einstein. We talked about him in the very beginning of our talk. So Albert Einstein first proposed a theory called general theory of relativity. Those of you who are in the college level, I'm pretty sure you have studied special theory of relativity. This is nothing but a generalized version of that, and this actually replaces the Newton's law of gravity, which you study in your high school level. So this is the better theory of gravity, so to say. I'm not going into the details of that thing. Using geometry and all these things, he has proposed this thing. But in 1905, for the first time, Einstein gave a modern version of theory of gravity, so to say. And then what happened? For the rest of 100 years, the most mysterious things we are going to observe, they are either related to the theory of gravity or quantum mechanics, or an advanced version of quantum mechanics, which you call quantum field theory and all these things. So for this moment, I'm mostly concentrating on the general theory of relativity. So what are the surprises we have been able to observe for the last 100 years or so? First of all, using this, Einstein himself explained that the paths of planets around the sun, they are not elliptical. This is a pretty surprising thing. Once again, from our high school knowledge, we know about Kepler's laws and all these things. We know that planets rotate around the sun in elliptical paths and all these things. We have known about that, 3 Kepler's laws and etc. But experimentally, much before general theory of relativity, it has been observed slowly and slowly that no. The paths are at the leading order, more or less, they can be elliptical, but they're not exactly elliptical. There is a slight drift of path after each rotation that has been observed, but nobody could explain that thing using Newton's law of gravity. Einstein, for the first time, proposed his new theory of gravity, which is theory of relative. This thing, not only that, he did quantitative estimations, which matches the experimental results for Mercury, which is closest to the sun. The perihelion, the path of perihelion and precession of Mercury, that matches to the experimental result and theoretical prediction, that matches to a huge extent. Okay, so this essentially gave the Einstein's theory of relativity much fame, but after that, there is more surprising that I'm waiting. Okay, second prediction of general theory of relativity is even more surprising, that it basically tells you the objects who are located further away from you, they will look more red. Okay, this is once again pretty surprising, because this is not something what we see day-to-day life. Okay, we see that objects are here, objects are moving, they can look smaller and smaller and all these things. But here what we see is that by these objects, what we mean to see is that they are astronomical objects, they are galaxies and etc. So they are further away from us, and if they move further away from me, then if I look into them using our telescope, we will see that they look more red and red. So their color, basically, there is a drifting towards red. This is typically a technical thing that I'm showing. I'm not going to the details of that, but those of you who have done spectroscopy in your physics laboratory, you can look into this and you can readily check that the bottommost column that gives you the laboratory reference of different colors of different wavelengths, the VGO kind of thing. And as the star from bottom to top, if you go along from bottom to top, you can see that as the star and galaxy and all these things, they are further and further away from us, the wavelength is basically being stretched. So it's similar kind of wavelength stretching, just like Doppler effect. I'm pretty sure you have heard about Doppler effect in your high school kind of knowledge. So it's similar kind of wavelength stretching, but this is not Doppler effect. This is a completely different kind of thing. This is called redshift. That happens due to the evolution of our universe and all these things. I'm not going to details of that, but all I want to stress upon is that this was the first surprising thing of Einstein's theory of general theory of relativity, and this was found experimentally to be matching exactly to the theoretical predictions in 1925. So in 1915, Einstein proposed that, and in 1925, this was first experimentally found out. And this has got lots of applications, which I'm not going to details. The third prediction is even more interesting, and this will be pretty relevant in our today's discussion, that using general relativity, once again Einstein predicted that light ray can be bent by gravitation. Why this is surprising? Because from our high school kind of knowledge, we have already heard about this. We have read these things several times that light travels in straight line. For sure, light travels in straight line with a speed which is the speed of propagation of light in vacuum. We know this is c. But for the first time, Einstein said that if I have a very strong gravitating object like stars and galaxies and all these things, then if a light ray which is coming from far away and that tries to graze away, that tries to basically move pretty close to this gravitating object, which is a star or galaxy, then due to the gravitational pull of this star or galaxy or whatever I call it, okay, I'll talk about black holes later on, but this is a gravitating object. Due to this its gravitational pull, the path of light gets bent. This is pretty much surprising because this is something we have not yet heard about. Hold on. Have you heard about this or not? Yes. If you think about this critically, then you have heard about that. You know about lenses in your school life. So when we say that light travels in straight line, you basically say that if there is no interfering medium, then light travels in straight line. But if there is an optical medium inside, like a lens, then a lens can basically bend the light, bend the direction of light. Just by similar argument, here, all Einstein wanted to propose, and later on we have found out this experimentally several times. As I said, this was found experimentally back in 1919, and this basically brought Einstein to an instant fame, so to say. So this basically tells you, Jay, that along with the optical lenses, any gravitating object, an object which has got huge amount of mass, it can act as a lens, and stronger its gravitational pull, the bending of light becomes more and more severe. So this is something new, okay? Because so far as Newtonian gravitation is concerned, we did not know that gravity can bend the direction of light. But for the first time, using general relativity, we have been able to first theoretically show and then experimentally verify that this is indeed happening. And this will play a very crucial role in today's discussion. So all these things have been experimentally verified 100 years back. But what about black hole? This is something which is a still surprising thing left over there. There are other surprises as well. I'm not coming to that, but I'll mostly focus on black holes right now. Okay, so let us right now. So this is the starting point of our theoretical discussion of black holes, so to say. Okay. So as I said, once again, in 1915, Einstein, for the first time, proposed general theory of relativity. Just after 1 year, a scientist called Carl Schwarzschild, okay, who basically went to a battlefield and all these things during that time, and then he came back and he was there in a hospital, and in the hospital bed he did this calculation. Okay, see the fun. Okay, scientists always they do their scientific research no matter where they are located. Okay, in the hospital bed, he did this calculation just after 1 year of proposal of general theory of relativity. And he proposed that using his calculations, he proposed that in our universe, there can be objects with huge mass and very tiny size. Once again, this is something new. In general, what we see in our day-to-day life, in our tabletop experiments and all these things, the object which has got higher mass, its size is bigger. This is something happens more or less. Okay. But for the first time, he said that in our universe, there can be object of which the mass is huge, but the size can be very, very tiny. If this is true, so this is theoretical development. That's what I'm trying to tell you. I will once again come to the experimental side later on. If this is true, then this basically tells you that they have very strong gravitation because a huge amount of mass is concentrated at a very tiny point. And since you know the object, whichever has mass, that shows you gravitational property. So essentially, they have very strong gravitation. And what we have learned just from the previous slide, from this slide, what we have learned that the object which has got stronger gravitational field, that basically bends the path of light more and more. So since these guys have huge amount of gravitational pull located at a very tiny point, so now if a light ray comes to pretty close to these objects, they can bend due to their huge gravitational pull. They can bend the path of light ray to a huge amount so that it basically, so the angle is greater than 2 pi. Okay. So if it is greater than 2 pi, it basically, the light ray gets basically trapped by its gravitational pull. And they can basically, at the end of the day, they can eat up everything. So if it can basically trap light, it can trap any other material as object. So essentially what we can say is that since it traps all the light, whoever is coming pretty close to it, so it cannot basically see them, because in order to see them, it should emit. This is from our high school kind of knowledge. Once again, it should emit sunlight. But since these objects, they can trap light and they can eat up everything around them, so that's why they cannot emit any kind of light. So at the end of the day, the conclusion is that we won't be able to see them directly, and that's why when I gave you the picture of Messier 87 galaxy, the black hole inside the Messier 87 galaxy, I told you that in the inside there is a black region which you cannot see. All we can see is just the boundary of that black region. Okay, so that's all about this thing without going into the mathematical details. 10 years later, in 1926, Eddington, Finkelstein, and Truskell, these three scientists, they gave somewhat a mathematical argument of Schwarzschild calculations, and they gave some explanation. They basically gave some explanation why at all this can happen. Okay, why this kind of funny, mysterious thing that can be present in our universe, and why at all they can behave like this. This is pretty unusual kind of thing we're getting. This is pretty mysterious kind of thing. Okay, so for the first time in 1926, these three guys, they explained this thing mathematically. 5 years later, in 1931, an young Indian grad student called Subramaniam Chandrasekhar, he first proved that these objects which can trap light in a very small region, these objects should have mass of at least greater than 1.4 times of the solar mass. So their mass should be at least greater than 1.4 times, and nobody believed him, simply because he was a young grad student of your age or so at that time, and nobody took him seriously until and unless in 1939, three famous scientists called Tolman, Oppenheimer, and Volkoff, they give a very rigorous explanation of Chandrasekhar's derivation using gravitational collapse and all these things, and they said that no, whatever Chandrasekhar is saying, that is perfect. And right now, this goes by the name of Chandrasekhar limit. Even in statistical mechanics, those of you who are studying statistical mechanics, you know there is a chapter over there where this Chandrasekhar limit and everything is being discussed. So this is a textbook material right now. Okay, so these brought Chandrasekhar to instant fame once again, but hold on, I'll come to his discussion later on. But at least for this point, people were getting convinced that in our universe, there should be objects like this, which are really, really funny and mysterious, but that has to be there because using our background theory, we are being able to explain their dynamics and explain their evidence pretty well. But then, in 1958, something new happened, which is pretty relevant in today's discussion. Once again, a young grad student called Victor Ambrutsumian, he, in a conference, for the first time, he argued that in each galaxy, there is a center of galaxy, and that center must be made up of huge mass. He did not give it a particular name. He called it active galactic nuclei, because nuclei means it's in the center of galaxy, and this is active because something dynamical thing is happening over there. So in 1958, for the first time, this guy said that in every galaxy, we talked about millions of galaxies, and for the first time he said that in every galaxy inside that, there must be a huge mass, which he called active galactic nuclei. After a few years, in 1965, Roger Penrose, you have heard about him, I'm pretty sure you have heard about him, and you have heard about him in the beginning of today's lecture as well. He basically shared the Nobel Prize of 2020. So Roger Penrose, for the first time, explained how black holes are formed mathematically by proposing something which is called singularity theorem. Once again, I said that I'm not going into details of the mathematical aspects of all these things because they are pretty complicated. Okay, but trying to give you a state of art feeling of the theoretical development of these things before going to the experimental aspects. Okay, so he proposed something which is called singularity theorem, which is pretty important in today's context. I'll come to that point later on. After 2 years, 1967, John Archibald Wheeler, for the first time, gave the name of these objects of black holes. There are several reasons, there are several stories why it was named as black hole. Some say that this is related to the infamous the black hole incidents that happened in the British India. Some say that no, this was given the name of black hole because this does not emit any light, so this is black and this looks like a hole and all these things. So forget about the origin of the name. At the end of the day, this funny name black hole, okay, there are debates about this name and all these things. You can find this thing in the literature. But this funny name black hole, that became very, very popular. And for the first time, people tried to believe that objects like black holes, which have got these funny properties, they must be present in our universe. During 1967 to 71, different guys, some of them are Warner Israel, Brandon Carter, and etc., they showed that these black holes have far more funny properties than what is expected. They said that these black holes can show only three characters. One is their mass, the other one is their charge, and the third one is spin. So only three properties they reflect. Whenever, as I said, black hole can trap any matter, even light. So whenever an object which goes pretty close to black hole, I come to that point later on, that gets trapped by black hole and it falls inside the black hole. Whenever it falls inside the black hole, it forgets about its existence. All it retains is its mass, charge, and spin. So all the other properties we have talked about in our day-to-day life, about different properties of matter and all these things, everything vanishes. And inside the black hole, only three properties are being shown: mass, charge, and spin. And some say that Wheeler, but some say that Bekenstein is also responsible for giving it a name. This is called no-hair theorem. Black holes have no hair. This is what is called no-hair theorem. Means essentially all the other properties are getting vanished. Some call it theorem, some called it conjecture, because this was not strictly derived. This was sort of conjecture. But more or less this is true so far as today's observation is concerned. There is no experimental violation of this thing. In 1967, let's go back to this guy, Victor Amratsumian, who in 1958 said that inside each galaxy, at the center of each galaxy, there should be a huge mass. In 1969, Donald Lynden Bell, who expired last year only, so he proposed that every galaxy contains at its center that active galactic nucleus that must be a supermassive black hole. What do you mean by supermassive? Essentially, as we have said already, that Chandrasekhar said that the mass of the black hole should be at least greater than 1.4 times of solar mass. Now, supermassive essentially means its mass must be huge amount, far greater than solar mass. I'll talk about the mass, exact amount of mass later on. But Donald Lynden Bell for the first time proposed that inside each galaxy, at the center of each galaxy, there should be a supermassive black hole. This is how the experimental side is also being directed. See the fun. Theory and experiment, they go hand in hand. Here theory is proposing something, and experimentalists, they are basically trying to find that thing experimentally. So the guiding direction over here is that go and try to find out, go and try to search. At the center of each galaxy, you will be able to see one supermassive black hole, or at least its direct or indirect evidences. This is the take-home message right now. I'll come to that point later on. In 1970, Hawking and Penrose, they gave a more concrete singularity theorem. And when we say that Roger Penrose saved the Nobel Prize, had Hawking been alive today, he should also have been awarded the Nobel Prize for the same reason, because they are on the same footing. They gave the more concrete singularity theorem. Unfortunately, Nobel Prize is not given postmouthly. So since Hawking is no more, he was not given the Nobel Prize right now, but he shares the equal credit. In 1974, Hawking and Bekenstein, they showed that even though black hole can absorb all whatever is there in the outside of its event horizon, it can basically absorb all of them, but there can be slight amount of radiation because of air production. I'm not going into details of all these things, and this black hole radiation, in once again Hawking and Bekenstein's brainchild, and this is still a theory. We have not yet been able to detect that, but we do hope that someday we'll be able to detect that as well. After all these developments, let's go back to 1931. This Chandrasekhar guy, when he was just a graduate student, and he proposed that the black hole mass should be something like this. From 1931 to 1983, he had to wait. And in 1983, Chandrasekhar was awarded the Nobel Prize in Physics for this. So see how the development of science is being done. It's not being done overnight. Okay, you cannot just expect something happening overnight. In some day you will just wake up and you will say that something I've been able to see. Okay, behind every success there is a huge and several years of developments by different guys, and at the end of the day something concrete thing happens in science. And this is what happened. And after that the experimental searches began. Okay, so how much time do I have? Any feedback? Excuse me. May I know how much time do I have?
Okay, carry on.
Okay, fine. So I'll take another 10-15 minutes. Is that okay?
Yeah.
Okay, great. Thank you. So, getting you bored, I'm basically trying to get you bored by this theoretical description and all these things. But all I want to stress upon is that it's 100 years of development from the theoretical side. And I mean, even after development, the mysteries of black holes, they are getting bigger and bigger. So from theoretical side, we say that lots of new things are happening around the black holes, and that those black holes, the scientists predict that they must be present inside every galaxy, so to say. So now the experimental search has begun, and I'll basically focus on that thing. So forget about the theory part. Right now I'm coming to experiment and then pictures and all these things. So back to our galaxy Milky Way. As per proposal of Lyndon Bell and all these things, that inside our galaxy, I said that our galaxy is made up of millions of stars and all these things, but inside there is something. I talked about this, that inside there is something. I'll come to that point later on. Now this is the right time to talk about that. Inside our galaxy, Milky Way, there must be a supermassive black hole as per theoretical predictions of different guys. And this Event Horizon Telescope, what these guys basically were trying to do is to find out the supermassive black hole inside our Milky Way. As I said, they have already found out this thing in Messier 87 galaxy. But at the same time, this is a theoretical prediction that inside our galaxy, this is artist's impression. Okay, this is not a real one. This is artist's impression. All it says is that if this is the galaxy, that inside it there must be a black region, which is a black hole. Okay, so this was the theoretical prediction, and these guys, the Event Horizon Telescope guys, what they did is that they tried to find it out for several years from 2009 onwards, and in 2019, in the same day, they released these two results simultaneously, that they've been able to find out a supermassive black hole inside the Messier 87 galaxy. Not only that, they have been able to find out the real image or shadow of a black hole, which is at the center of our own galaxy. The name of the black hole is called Sagittarius star. See how surprising this is. We are living in a galaxy. We are living in a solar system, which is a star inside this galaxy. And at the center of the galaxy, there is this huge amount of, in terms of mass, okay, huge amount of black hole, which is supermassive, that is sitting over there for several, millions and millions of years. And basically, that is why this is exciting. This is the time we have been able to see that for the first time. So we're living in a pretty exciting time so far as scientific research is concerned, that even if that is there for millions and millions of years, today, just 2 years back, we've been able to see them directly for the first time. And how much is the mass? I said that I will talk about the mass. The mass of Sagittarius A star is 4 million times than the mass of star. So it's 40 lakh times heavier than the solar mass. So it's a huge mass. It's a huge mass. It was located inside our galaxy for millions of years, and for the first time in April 10, 2019, we have been able to see once again, we have not been able to see the black hole directly. All we have been able to see is the outer surface of the black hole, which is called event horizon, and loosely speaking, this is called black hole shadow. So this is a real image we have been able to find out. I'll show you some videos in a minute, but before that, this is how it behaves. These are the pictures of different times taken for the last 10 years or so. And last 10 years or so, all of them are not real images. Some of them are basically projected geometrically, but some of them are real images as well. I'll come to that point later on. But this, just to keep in mind that this is something that has been experimentally found out. So when I used to give talks on black holes 5 years back, my job was much more difficult, because if someone asked me, you have talked so much about black hole, but have you been able to see black hole yet? My answer would have been, no, not yet. We have been able to see, but we do hope that someday we'll be able to see. But right now, my job is much more simple, because right now I'm pretty confident, and I'll answer to this question with an affirmation that yes, of course, we have been able to see black hole, not directly the black hole, the shadow of the black hole, even in our own Milky Way galaxy. Okay, so this is pretty real experimental phenomena. This is no more a mystery. I mean, mysteries are there for sure, but this is no more something which cannot be there. It is there in our galaxy and in all the galaxies as well. So there are lots of black holes in our universe. Okay, so how does it all happen? This is about technical things. I'm not going into details of that. Instead of that, what I will do is that I'll show you a video, a small video. This is a very small scientific video. I just show you for the first time, and then I'll explain what it means. So just try to look into this video for the next 1 or 2 minutes, and when this video will be going on, just try to listen to me. I'll try to explain this video in simple language, slowly and slowly. So this video basically tells you how a black hole formation is done, how basically black hole traps matter around it, which is going pretty close to it, and how this event horizon is being formed, and at the end of the day, how we have been able to see the black hole. Okay, so hold on, this is the beginning of the video. Yes, see, suppose you are someone who are going from, this is a hypothetical experiment. Suppose you are going from the Earth's surface towards the black hole. You see lots of, inside the galaxy, you see lots of stars, and here, this is something called accretion disk. This is something which is formed. Inside you see a black hole, and outside you see accretion disk. By this disk, it basically catches all these, everything that is moving inside this. And now we are going far more closer to this thing, and all they are moving at each are stars. Okay, so each star is moving around black hole, and due to their movement, they are basically coming closer and closer, and they form something which is this. This is called the event horizon. All these stars, they are there, they are aligned at some particular direction, and you see the event horizon. Inside this event horizon, basically black hole is basically catching, everything is there, and at the end of the day, you see this event horizon image. So as you see, this is called the image. Let me go back a little bit and show you that the previous results, they are computer simulations based on our theory. This is called simulation. Let me stop over there. This is called simulation. So don't just confuse with all these things. The image, final image, you have been able to see, because this is something that is happening over millions of years. Okay. So in 1 day or in 10 years, we won't be able to see everything. But we have been able to see the end point. That is pretty real. And before that, we have done everything by computer simulation based on our theoretical calculations. I'll come to that point. So since the end result matches, we are pretty convinced that all this dynamics is really true. And whatever we have been explaining using black hole formation, that is actually the correct thing. Okay, so these are simulations up to this point. And at the end of the day, this is the real image, EHT image. Okay, this is something we have been able to see. So that's how this is a pretty I mean, to cut it short, even though I discussed it in a bit details, but I tried to basically, sorry, just a minute. I tried to basically avoid the complicated mathematical complications over there, and I tried to focus mostly on the storytelling mode, so to say. I'll take another 5-6 minutes or so, and I'll finish. But at the end of the day, what I want to say is that black hole is a reality. This was a mystery for the last 100 years. Everything had been developed theoretically, and theory gave us a particular direction to search for that. And using those hints, people tried to search for those black holes, and they have been able to find out those black holes. So this is no more a mystery so far as theory is concerned. There are lots of other mysterious things happening in the black hole that we do hope that we'll be able to see later on. But at least right now, we can say that yes, black hole is a reality. Okay, and it has been a reality only pretty recently. Okay, and because of that, let me come back to this Nobel Prize business. These two guys on the right-hand side, they got the Nobel Prize because they basically led this experiment. They got this Nobel Prize, the half of this Nobel Prize, for the discovery of the supermassive black compact object, which you know, this is supermassive black hole for sure at the center of our galaxy. So this is what happened in the last 2 years. Now, how do we extract information using telescope? A scientist's perspective. Once again, I will not go into the details, but I do hope that some of you who are present in today's talk, some of you will take up scientific research as your career, and this is just to give you a pathway of what these guys exactly do, so that you can get some interest in this field, or you can get demotivated as well, depending on whether or not you find my talk interesting. Okay. So this is what we actually do. We do not directly we do not look into the sky and say that this is the black hole. It's not that simple. Our job is much more complicated. And I'm going to discuss about these complicated things slowly without going into details. So first of all, what you do, I mean, this is not only true for black hole, this is true for any astronomical phenomena or the cosmological phenomena as a whole. So whenever we do astrophysics and cosmology using our telescope, what we do is that the first step is that we collect raw data using our telescopes. All these hundreds of telescopes we have been discussing, using those telescopes, we collect raw data first of all. Why do I call raw data? Because the data, the waves are coming from far away. In between, they traverse different paths, lots of other things are happening, and all these things basically disturb the properties of the wave. Okay, so what do I call it in scientific language? They are basically noises. In laboratory, whenever we do experiment, we see noises. Like when you see FM and all these things, you see some noises coming. So you need to tune that properly. The same thing you need to do over there. So what we do is that we collect the raw data, and then we do noise reduction technique. We basically employ noise reduction technique, or in technical language, this is called cleaning. So we use different statistical techniques, okay? We use different statistics, and why I'm talking about that, because you will see that lots of different branches of science, they come hand in hand. You will see physics, you will see mathematics, you will see statistics, and you will see computer programming as well. So all of them are involved over there. So using statistical techniques, we basically do noise reduction, and we try to extract out the scientific data. We tune basically. So this is the kind of tuning we use. Out of this raw data, we extract out scientific data. Once we have scientific data in our hand, we try to analyze that scientific data using statistics and computer programming. In our computers, it's not a pretty simple computer we use. We use high-end computation with different numerical codes and all these things. So computer programming is pretty important. So far as today's research is concerned, all of you are pretty aware of that. You must know computer science in order to do research in these fields. So we do computer programming, we do coding and all these things using background statistical techniques, and then we analyze this scientific data. Once we analyze this scientific data, what we need to do in our laboratory when we do the experiment, we do error calculation, right? In our high school level, from our high school level, we know whenever we do experiment, there are some errors they creep in because of the instrumental error, because of the manual error, because of other errors and all these things. Here also, we are doing some experiment, we are catching the data, and there can be lots of sources of error. So we need to estimate the error as well, okay? Because once we can talk about the error, we can say how convincing, how confirmatory our results are. So not only we need to talk about the data, we need to talk about the results, but also we need to estimate the error using statistics and computer programming. Once we do that, we finally scientifically draw, or technically this is called mapping, the image with high precision. So whatever image you are being able to see, they are not the direct images. Whatever image you see about our universe in popular science lectures or videos or social media or whatever picture you see, they are mostly not the real pictures. But they are the real pictures, because whatever we see, that is the raw data. We basically decode that raw data scientifically, and at the end of the day, we draw the image. And we say pretty convincingly, because we have been able to estimate the error as well. So we say pretty convincingly that this is the real thing that is happening over there. So using our data, because we are using different kinds of telescopes, so using our data, we basically draw the image, albeit scientifically with high precision level. The error is really, really small. Because if I cannot give the results with high precision, you are not there to believe me. Whenever I say this is the fact, you need to believe me. So I need to make you believe with my error estimation as well. And then the rest of the things that remains as a physicist is that using your knowledge of physics and all these things, and you do computer simulation as well, the kind of simulation I've already shown you, using your background knowledge of physics like general theory of relativity, quantum mechanics, quantum field theory, statistical mechanics, whatever you study, okay, you basically combine all of them, and you build your theory of astrophysics and cosmology, and from there, you basically interpret the data in terms of your physics, and you explain. Okay, so whatever we have been talking about from the theory side, so that theory must go hand in hand with what we find out in experiments. This is the last part you need to do using your theory. Okay, using your physics knowledge, and herein lies the basic rule of physics. So that is how this is that's why I said this is a synergy between theory and experiment. At the same time, this is a synergy between synergy among different subjects. Like you do experiments, then you do you do physics, you study physics, you do physical analysis, you do mathematical analysis, you do statistical analysis, you do computer programming, all of these taken together, and the end of the day, the gist is that picture so far as black hole is concerned. So it's all about this. Once again, I try to avoid the technical details, but at least up to this point, I thought I should give you an impression of that. Then I will take another 5 minutes or so, and I'll finish for you. Okay. So now the question is that, yes, of course, 2020 Nobel Prize was given because of the discovery of a supermassive black hole inside our own galaxy, as well as inside Messier 87 galaxy. But is it all? And is it the single evidence of black hole so far? The answer is no. We did have evidence of black hole earlier, and we do have evidence of black hole later as well. So I'll spend 5 minutes on this and I'll stop. I'm pretty sure you have heard about gravitational waves as well, which is another interesting thing so far as general theory of relativity is concerned. And this was also a mystery for the last 100 years or so. And this was the LIGO, this observatory that basically detected gravitational waves in 2015. Okay, so this is the technical details. I'm not going to the technical details. This is basically an interference experiment. You know for sure for waves they show 3 different properties: polarization, interference, diffraction, and polarization. This is the kind of interference waves, interference experiments. This is an interferometer, but it's a huge interferometer. The length of the arms are 4 kilometers, and I'm not going into details of this because my intention is not to discuss about gravitational waves in details. Okay, but all we did is that using this technique, we have been able to, the LIGO mission, LIGO and Virgo collaboration, they have been able to detect gravitational waves for the first time in 20, this is, let me skip this part, they have been able to detect gravitational waves for the first time in September 14, 2015. And from here, once again, we had our theory, we had our simulations and all these things. As I said, we need to make a synergy among all of them. And when we try to match these two, the conclusion is that these gravitational waves, they have been generated, whatever you can see, there are 2 black holes, there are 2 holes over there. This is not a real picture, as I said. Okay, so this is a simulated picture. So we have 2 black holes, and they are basically, since both of them have huge mass, they are basically they come pretty close and they attract each other, and at some point they basically collide and form a single black hole. Because of this collision and formation of single black hole, as I said, their properties are only mass, charge, and spin. All the other properties they will forget. And because of this difference in mass, charge, spin, and all these things, they basically emit gravitational waves. So we've been able to detect that gravitational waves in LIGO in September 14, 2015. And from here, for the first time, we got indirect evidence of black holes. This basically tells you, since I've been able to detect gravitational waves, and I have my background theory, I have my simulations that matches with the with this kind of physics, so you can claim that these gravitational waves have been generated from the merger of 2 supermassive black holes. So these were the first time where we got indirect evidence of black holes. And then I'll spend 2-3 minutes on the last and the most recent observation of evidence of black holes, so to say. This is the European Southern Observatory. This is located at Chile, far west, sorry, far south, in North America, at Chile, South America, sorry. And this is called European Southern Observatory. European Southern Observatory is there, which looks like this. And I will talk about, this has got different kinds of telescopes inside it. I will mostly concentrate on this telescope, which is called Very Large Telescope, VLT, which is a part of European Southern Observatory. This is an optical telescope, keep in mind. Okay, so far I talked about the Event Horizon Telescope, which was a radio telescope. The waves it caught, basically its intention was to catch, their wavelength was pretty larger than the optical. But this one, the waves it will attempt to catch, or it attempted to catch, it has already found it out, they are in optical region. So they are pretty simple optical telescope, albeit the technical complications is much higher. It's a combination of 4 different optical telescopes, which you can see over there. They combinedly, cumulatively, they give you the result. Okay, so this is once again the technical complications I'm trying to avoid, but this is what they found. Okay, if you recall, when I discussed about general theory of relativity, I said that the first success of Einstein's theory of relativity is that he could explain the rotation of the paths of planets around the sun. Okay, which is not exactly Keplerian for sure. That was explained. Now, if that theory has to be valid, then the conclusion is that if I have a heavy object somewhere, that is a black hole, and if the stars are rotating around the black hole, then their rotation, their paths will also show similar kind of effects. Okay, this should not be exactly elliptical. They should also drift the path. This was the calculation. Okay, and I have also already shown you the simulated results earlier. But this, for the first time, the photo was taken by very large telescope, the optical telescope, as I said, in April 16, 2020, just last year. And just pause a minute once again and try to think over it. April 16 last year, during that time, the coronavirus, SARS-CoV, that was dominant throughout our universe. All of us were there inside our safe home, either maintaining lockdown and all these things, or we have been pretty afraid of what will happen to us. And here's a bunch of scientists who, at that time, they have been doing scientific research. Not only that, they have been doing this thing for the last 30 years or so. So the image you see over here, it's a superposition of image. I'll show you a very small video for that. This is a collection of 30 years of result, and the result was published only last year when everybody was afraid of coronavirus. They were in pretty safe home. But as I said, why I'm stressing on this thing, as I said, the advent of science, the development of science is still going on. Even if during this situation, everything is stalled, the advent of science, that is still going on. Okay, and that proved Einstein's general relativity correct once again, because that was once again a direct conclusion for general relativity, and this was experimentally found. Okay, so once again, this was a direct evidence of black hole, albeit the fact that we could not see black hole directly because we cannot, but we could see the paths of black holes rotating, paths of stars rotating around the black hole. So this is a 25 minutes, 5 seconds of slide that I'll show. This is once again a simulated result, but this is what exactly they have observed for the last 30 years or so. This image was released. Okay, so this is how things are happening. So this is a single star that is rotating around a black hole. You can see a black dot inside. So this is a single star, and after one rotation, it basically drifts its path. It does not come back to the same elliptical path. It is drifting. This is called precession, perihelion precession. This is something every planet rotating around every star shows. This is something every star rotating around black hole shows. Okay, so this is how its paths look like. And this is what we have been able to see. I'm almost at the fag end of my talk. This is something what we have been able to see only in the last year. See how exciting the time is. Once again, I'm stressing on this fact that you guys, especially the younger ones, you are living in a pretty exciting time because you are going to begin your research career. And if you choose this field has been never more exciting than today. Okay, all the theoretical developments that have been done for the last 100 years, there are some experimental results earlier and all these things. But right now, only in the last 5 years, we have got 3 completely different evidences of dark matter, of black holes, so to say. I'm skipping this part because I don't have much time to discuss about Roger Penrose's work. This is much more complicated as well. So I'm skipping this part just to show you that thing that Penrose gave a very strong mathematical description of this thing based on the Minkowski diagram, and this was generation of Minkowski diagram that we read in special relativity. And our own Indian scientist, a Bengali scientist called Amol Kumar Raichaudhuri, I'm pretty sure you have heard about him for the last few days or so, or 1 year or so, because the Penrose's calculation, Hawking's and Penrose's calculation, that was mostly based on something which is called Raichaudhuri equation, and this equation was proposed by or developed by, I'm sorry, I don't have much time to discuss about his life. This is pretty fascinating life. When he was a grad student, once again, the grad student life is pretty important. The earlier age, that is pretty important for path-breaking research. So when he was a grad student, he did these calculations all by himself, and he published this in the journal Physical Review that time. And this came into limelight by the development of Ellis and Hawking and all these things. And the Penrose's research, Penrose's Nobel Prize, it has got a very strong contribution from Raichaudhuri equation, so to say. It's singularity theorem that was mostly developed based on Raichaudhuri equation. So he has got a pretty important role in last year's Nobel Prize as well. So all said and done, I'm not sure if you enjoyed my talk or not. I'm not sure if I was too descriptive. I said so many things, I'm not pretty sure. But I tried to keep your light as simple as possible, even though it may look much more complicated, but it's actually much more complicated than what you see, but at the same time much more exciting as well, because here lies the excitement of doing theory, doing mathematics, doing computer programming, and doing experiments as well. And of course, in the process, knowing about our universe, which is of course the most fascinating thing. So here lies the bottom line of black holes. It was predicted 100 years back, and it was discovered pretty recently by not only by one experiment, but by 1, 2, and 3 different experiments. So in the last 5 years or so, we have 3 different experiments by which we have been able to directly or indirectly say that in our universe there are lots and lots of black holes. So black holes are no more mysteries, even though there are lots of other mysterious things around black hole, which you guys need to explore if someone of you take up this as your career. But this is no more only mystery. This is something which is reality, and this has become reality in very recent past. We have been able to do that. We have been able to see that. So this is just a slide I usually show to the younger guys. If you want to make it your career, what you need to do is that you need to have very, very passion towards the subject. You need to be very, very passionate. Okay. And after that, you need to do very, very small things. You need to study BSc in physics and mathematics. You need to have computer science knowledge, and then you need to do MSc in physics, applied mathematics, or astrophysics, or at the time you can do specialization in astrophysics and cosmology. After that, you need to do your PhD and postdoc in astrophysics and cosmology. When I say grad student, your grad student life starts during your PhD. During this time, you will be able to do new things, and maybe, who knows, someone of you who are basically listening to my talk today, you will be able to discover once again a new path-breaking discovery, so to say. And so this is the end of my talk. As you know, I'll quote Shakespeare. What is said in Hamlet is that there are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. So our universe is much more surprising, much more fascinating than whatever we can think or imagine or we can write in poetry or literature or even in mathematical language. Our universe never stops us to surprise, and our job as scientists is not to achieve something, but to enjoy these surprising things in much more concrete language. And that's the purpose of doing research in this field. I'll stop over here. Sorry for overshooting, and I will take up if you have any question. Thank you very much for your kind attention.
Yes, indeed, that was really mesmerizing. Thank you, Professor. So, any questions?
If there is any question in the chat box, some of you.
Sir, I have a question.
Yes.
So, how can light be bent if light has no mass?
Yes, that's pretty interesting thing. That's pretty interesting thing. And because of that, you need to do a little bit of mathematics of general relativity. Okay. So, even in special relativity, you know the rest mass of photon is 0. When you say, I mean, first of all, so the question, I guess this is coming from a UG science level student, right? So you have some idea about special relativity. Is it okay?
No, sir, I have no idea about special relativity, but
I'm sorry, that will be even more difficult. So I'm trying to give very simple explanation, but if you don't have knowledge of special relativity, it will be really difficult. Special relativity says that, so you know light is a stream of photons, for sure you know that. And special relativity basically proves, experimentally, both theoretically and experimentally proves that when I say that light has no mass, it essentially tells you the rest mass of photon is 0. Whenever this is at rest, it does not have any mass. But if it is moving, it attains some mass. So it does have some mass when it is moving. When it is at rest, it does not have mass. So now, since this is moving, a light ray is passing, means photon is moving. So it does have some mass. It's not that simple as well. As I said, when we do this thing using general relativity, what we do is technically this is called null geodesics. You are studying. I'm sorry, I'm talking about this technical jargon, but Unless that is being told, I cannot explain that. So you study null geodesics. Null geodesics essentially tells you the paths of photons, the streams of photons which are moving. Okay, and since they are moving, they've got some mass. So streams of photons which are moving, and we try to find out the null geodesics of that. Okay, their trajectories we are trying to find out. Okay, and these are the trajectories we see if the photons are moving pretty close to a very massive object, say a sun or a black hole, then because of this its gravitational pull, their paths are basically getting bent. Okay, this is, I'm trying to tell you in very simple language. I'm not sure I could convince you or not, but I can assure you that if you know a little bit of special relativity and general relativity, this will be very obvious to you. Okay, thank you for the question. Any other question? I will request the organizers if you can read out some of the interesting questions from the chat box. Then, I mean, it's your choice. I'll try to answer to that if you have time.
Yeah, there is a question in the chat box. Udit Roy, he writes, what about wormhole concept of black holes?
Okay, once again, these are pretty funny names, and I'm pretty sure you come across these names in your day-to-day life, I mean, in your popular science talks and videos and all these things, or books. But once again, this is a pretty difficult thing to explain, wormholes. In simple language, wormholes are even more surprising things compared to black holes. And so these are, once again, I'm not going into the technical details. I did not go into the technical details of black holes as well. But wormholes are basically, they are much more complicated than black holes. And all it tells you is that wormholes make you possible to have time translation. I mean, this is called the time travel, so to say. Okay, in your fiction and all these things, if you have watched the Interstellar movie, you have seen about time travel and all these things. So mathematically speaking, just like black holes, wormholes are even more complicated, more funny astronomical objects, of which we have got the theory developed. Okay, and the theory says that if there are wormholes, then time travel would be a real thing. Time travel would no more be a fiction. Okay, till now we know time travel as fiction, but if someday we can, we are able to detect wormholes at some point, then time travel would no more be a fiction. Time travel would be a reality. But till now, all I can say is, I should be honest and I should say that wormholes are much more complicated things than black holes, which are proposed mathematically. Just like black holes have been proposed, wormholes have been proposed, but we have not yet been able to detect that. Okay, but we do hope that just like black holes, we have been able to detect that, someday we'll be able to detect wormholes as well. Okay, this is something I can tell you in a very simple language. I'm sorry I cannot discuss about the mathematical jargon. I'm sorry. Okay.
Hello, sir.
Yes,
I
yes.
was asking that, wormholes are fictional. Like, are they totally fictional in these days? Like, they have some mathematical basis, but are they totally fictional, or they?
No, I don't say that it's fiction. Okay, that's the point. Okay, let me reiterate. This is a nice question. Okay, this is not fiction. I was talking about two different things. I was talking about Interstellar and all the other things, all the science fictions. Okay, there it is fiction. But as I said, just like black holes were not fiction. Black holes were mathematically developed. Okay, but in science there are two aspects. You need to keep this in mind. In science, you develop something mathematically and then you do experiment. Until and unless you find it in experiments, you cannot say conclusively that this is there. Because at the end of the day, physics is an experimental subject. So just like black holes, wormholes are also mathematically developed. That part, theory part, there is no problem. The development is still going on, but there are lots of developments as well. So this is no more fiction. But until and unless we can visualize them directly, just like we have been able to visualize black holes for the last 5 years or so, until and unless we would be able to visualize that thing, all we can say is that they are some theoretical objects. We have been able to develop the theory, and we do hope that someday we will be able to detect that. Okay, so they're not fiction anymore. I don't say they're fiction. But until and unless physicists are really skeptic. Okay, they're never satisfied. They don't say that I have got a very good mathematical description and I'm happy with that. No, no, no. Even after that, they try to find it out experimentally. Okay, until and unless we are being able to find that out, and that too very precisely in different experiments, we won't say that that thing exists, to be honest. Okay.
Well, there are two more questions here. One is about the reference books that should be followed at BSc level, and another is that what is the evidence of existence of dark matter?
Okay. First question is pretty simple. At BSc level, in order to understand the physics of whatever I call it, general theory of relativity, black holes, dark matter, etc., whatever you know about that dark energy, in order to know that, at least you should know special theory of relativity, and then some kind of geometry, which is called Riemannian geometry. Okay, the simplest possible book that I can refer to you is, there are two books, I should say. One is by Sean Carroll. This is available in the website, and the book is also there, Sean Carroll. The other book is by T. Padmanabhan. Both of them discuss in a simple language the theory of general relativity and their applications. But I am afraid how much you'll be able to probe that at this stage. Okay, at BSc level, this is really difficult. Okay, you can have some non-technical books for sure. There are some popular level books and semi-popular level books, like Hartley is there. Hartley is a more or less a semi-popular level book. This discusses science, but not much mathematics. But in order to know the mathematical details from the point of view of a scientist, you must have those backgrounds of special relativity and all these things and Riemannian geometry. So you need to hold on a little bit. Okay. But so far as the reference books are concerned, of course, I can tell you three names. Sean Carroll, just to begin with, there are hundreds of good books. Sean Carroll, and then T. Padmanabhan. Padmanabhan have several other books. This is about gravitation. And the third one is Hartley, the book by Hartley. To answer to the next question, dark matter, this is not directly related to today's talk. Okay, you can find out, so you can just check YouTube and all these things. You can find out some of my video lectures on dark matter, dark energy, etc. Or you can check my website. There I have some slides, popular level slides. Don't go into the technical slides, which I discuss in conferences, all these things. But there are some popular level slides on dark matter and dark energy. You can just go into this, because this is altogether a completely new branch, which I don't have any scope of discussing at this moment. Just like, all I can say is that, just like black holes, dark matter and dark energy, they are also two mysterious things in our universe, of which we are having several evidences, indirect and direct evidences. Just like I talked about Vera Rubin, she found out some evidence, then Zwicky found out some evidence. Lots of other evidences are coming so far as cosmology is concerned. And there are lots of theoretical developments as well. So both we have theoretical developments and we have indirect evidences. But till now, we don't have direct evidence of dark matter and dark energy. So just that's why I said, I mean, the mystery is never stopped. The universe never stops you in surprising. Okay. So there are lots of other things that are yet to be known. There are some development, and that's why development is being done. There are some developments both in the theory side and experimental side, and there are lots of other things that need to be done. But since this is a completely new, completely different thing from black hole, and in order to explain that, I need sufficient time. I'm not going into that. If you're interested, you can check some of my video lectures that are available in YouTube, both in Bangla and English. Okay, thank you.
Sir, in the very last slide that you showed that any star that moves in an elliptical path, but it like every time it rotates around the black hole, it changes its path. So is it totally possible for sun to come very close to the black hole and then change its path?
Okay. So are you afraid that someday we'll fall inside the black hole? Is this the reason or what?
No, I mean the video was pretty fascinating, and that's why it came to my mind.
Okay, that's good. Thank you. No, I mean, to be honest, the distance between Sagittarius A star, which is the nearest black hole, which is the black hole in our center, the distance between that and sun, that is pretty large. That is pretty large. So right now there is no scope of sun rotating around that in those orbits and coming close to that, falling in the accretion days, and at some point merging into the black hole. There is no chance of doing that, at least in near future. Okay, this happens only for the stars which are pretty near to the accretion disk of the black hole. Okay, they are pretty near. Okay.
Okay.
So there are a few questions about why does the laws of physics not obeyed near the black hole, and
Who
another is
says
the
that laws of physics are not obeyed?
Shagnik Day.
No, no, no,
says-
Sir, I was asking that as per I know that the laws of physics doesn't hold within a black hole. So why
Okay,
is it there?
that's a good question. Let me try to answer that. Okay, that's why I say this is pretty. I mean, this is a pretty surprising thing, and they are pretty mysterious thing. But there is nothing unscientific over there. Okay, by laws of physics. Whenever you say laws of physics, you must keep in mind that this is your limitation. At some point, just like that, before Newton, nobody knew that the reason Earth is rotating around the sun. For the same reason, an apple is falling from the tree to the Earth's surface. It's the same reason, theory of gravity. So every time some experiment happens, and we try to build the law of physics in order to explain that. And vice versa. Sometimes the law of physics is there, it predicts something, and then there is explanation. Okay, so if you try to explain all these things using your old theory of gravity, which is Newton's law of gravity, you can never explain that. Because as I said in 1915 only, Einstein said that this is a better theory, and using that we said that Newton's law of gravity that has got some limitations, and we have been able to overcome that. So right now, by law of physics, all we'll say, so far as the astrophysics and cosmology is concerned, we'll say about Einstein's theory of relativity. And Einstein's theory of relativity generically predicts whatever we see in black hole. Everything, the predictions are there. And this is what I was discussing in between my talk. Okay, lots of theoretical developments. Okay, I did not discuss the mathematical aspects, but every piece of development that is based on laws of physics. So everything is over there, except for the fact, you mentioned a very interesting point, except for the fact when the object reaches the center of the black hole, which is called singularity, we cannot explain that using our general theory of relativity. Okay, so we should be honest and we should say, because that's why the name is singularity, and this singularity theorem and all these things that has been developed by Penrose, Hawking and others using Ricciardo equation, that basically tells you that a singularity is evident for black hole. That must be there. Okay, so as soon as something reaches the singularity, at that point, using our classical theory of relativity, classical theory of gravity, which is general theory of relativity, we won't be able to explain that, because there, the notion, the basic notion of special relativity and general relativity is space-time. Okay, if you know special relativity, you know space-time. We don't talk about space and time separately, we talk about space-time. So general relativity is also based on space-time. Now, this basic notion of space-time breaks down whenever you reach singularity. Okay, so classical theory of gravity breaks down, and you need to incorporate something to explain that singularity, which generically goes by the name, within quote unquote, this is called quantum gravity. Okay, there are lots of different proposals of quantum gravity, like loop quantum gravity, string theory, etc., etc. I'm not going into details of that, but using those quantum theories of gravity, people try to explain singularity. So there is nothing beyond. It's not like law of theory does not hold good. All it says is that the law of nature, it's not like law of nature does not hold good. It's just that law of nature still holds good. You need to explain that thing using a better law of nature. You need to give a quantum description of gravity in order to explain that. And there are lots of developments happening along that direction as well. I should be honest and say we are yet to achieve a foolproof theory, but we are in the right direction. So singularity is something which is yet to be explained, but it's not like something unusual happens over there. It's just that we need to have a better theory to explain that, and we are on the right track to explain that. Okay.
Okay, so there is another question. So, what is the concept of white hole, and is it anyway related to black hole?
It's just the inverse of black hole. Okay, this is still once again the mathematical description and all these things. It's just the inverse of black hole. Whatever we study, the inverse thing can happen in white hole. So just like black hole, it absorbs everything, and that's why this is black. Okay, we cannot see that. Mathematically speaking, white hole is something that emits everything. Okay, it does not absorb everything. Whatever comes to closer to it, it basically bounces it back. So everything is bounced back, and that's why this is called white hole. Mathematically speaking, this is just the inverse of black hole, and strictly speaking, once again, just like wormhole, I mean, basically, if you combine a black hole and a wormhole together, black hole and a white hole together, you can get wormhole. But I'm not coming into details of that. The mathematical developments are still there, but experimentally, we are yet to find out that. Okay, so simply put, a white hole is just the inverse of black hole, which, mathematically speaking, which emits everything it comes to near to it. Rather, it emits everything. That is why this is called white. Okay, but we are yet to detect that thing experimentally.
Hello,
Sir,
Yes, please.
Hello, sir. Actually, my question is, for every black hole, every types of black hole, is it confirmed that there always must exist a singularity inside?
Sorry?
For every types of black hole, is it confirmed that there must exist a singularity inside?
No, not that. That's not the thing. As I said, I tried to skip all those parts. I said that Tolman, Volkov, Oppenheimer, etc. They tried to explain this thing. They gave a mathematical expression which is called gravitational collapse. Okay, since already the organizers are telling that we should stop, so I'll stop this in a minute. Okay, so I'll just try to explain that thing in simple language. It basically tells you that a star, okay, whenever you have a star, just like sun, there are internal dynamics, internal combustion going on. That's why we are being able to see that. So it has got two basically forces which are acting opposite to each other. One is its gravitational pull, which is pulling it inside, and the other one is the pressure force, which is going outside due to combustion. At some point, it will exhaust most of its energy, and it will no longer be able to overcome, no longer be able to resist its gravitational pull. So due to its self-gravitational pull, it basically starts shrinking. And depending on, there are lots of mathematics over there, depending on its size and all these things, it can form a white dwarf, it can form a neutron star, it can form a black hole. All these things I'm not going into details, but a black hole is formed at some point as the death of a star because of its self-gravitational pull. And until and unless its size, its radius becomes something which is called Schwarzschild radius. Okay, I'm not discussing that thing in details. There is no scope of discussing mathematics. So whenever it reaches its Schwarzschild radius, it basically isolates itself from surroundings. That forms the horizon of it. It isolates itself from the surroundings, and there inside it, you see that there is a singularity. At that point, there is a singularity. Okay, so as soon as the black hole is formed, you talk about singularity and all these things, but it's not like when it was a star, okay, yet to collapse, there was no singularity, nothing over there.
Actually, okay. My second question is.
Just a minute. I should take permission from the organizers because I'm really sorry, but the organizers are saying that it should wind up things. I mean, is that so?
Okay, this is last question.
Okay, fine.
Sir, as we have the only mathematical existence of singularity, so and we know that any data can comes out from singularity. So in future, what should path we should take that to observe the existence of singularity?
Okay, that's yet to be known. That's a good question. Okay, I could have given you some answer, but I'm not giving you the answer just because to keep the curiosity. Because as I said, inside the event horizon, we cannot see anything. Okay, we can only see up to the event horizon. That is what we have seen using event horizon telescope. As soon as an object reaches the event horizon, it basically loses all its properties. Okay, it gets absorbed into the black hole, and it shows up only three properties: mass, charge, and spin. Okay, and we cannot. Nothing comes out of the inside of that event horizon. Nothing comes out of that. So we don't expect that we'll be able to see directly the singularity and all these things. I mean, nothing you'll be able to see inside the black hole. But maybe someday someone will come up with some experimental proposal by which, just like we are being able to see the event horizon, there might be some effect that by which we will be able to see the indirect evidence of those things at the event horizon or anything else. Okay. Till now, this is an open problem, and you don't expect, at least I should be honest and say, you won't be able to see the singularity directly, no matter how hard you try. Because of the simple property of the black hole is that as soon as you cross the event horizon, nothing comes out directly. Okay.
Okay, sir.
Okay, then now I would request Professor